Jai Hind everyone. In this lecture of the subject Electrical Machines 2 KEE 503, I am going to discuss a topic of synchronous machines, basically synchronous motors. I am going to discuss here the principle of operation of synchronous motor, three-phase synchronous motor, the starting of three-phase synchronous motor, starting methods for the same, and the V curves and inverted V curves for three-phase synchronous motor. So, starting with the working principle of the motor, we know that the synchronous motor works on the principle of magnetic locking. So, what is magnetic locking? Let us first understand this. When two unlike poles are brought near to each other, if the magnets are strong, a tremendous force of attraction exists between two unlike poles, right? In such condition, the two magnets are said to be magnetically locked. Let us consider a three-phase synchronous motor. I'll show the synchronous motor schematic representation on the next slide. Let us consider a three-phase synchronous motor whose stator is wound for two number of poles. The two magnetic fields are produced, one by the AC winding, which is over the stator or the armature winding of the machine, which is over stationary part of the machine, and another one is the DC supply given to the field winding, which is placed over the rotor of the machine. Let us first just revise the construction of a three-phase synchronous machine. The three-phase synchronous machine consists of a stationary member and a rotating member, as just like the other electromechanical energy conversion devices. The stationary member, which is the stator of the machine, carries three-phase armature winding, and the rotating member, which carries the excitation winding. The rotor carries the excitation winding or the field winding. The field winding is provided with DC supply, and three-phase armature winding is provided with three-phase AC supply. Let us see what happens when a supply is given to the three-phase AC winding of the machine. We know when a three-phase AC supply is given to a three-phase AC winding of the machine, a rotating magnetic field is created. The rotating magnetic field rotates at a constant speed. That constant speed is given by Ns equals to 120 F upon P, where F is the frequency of supply given to the armature of the motor, P is the number of poles for which the machine is wound. So, we are considering here the construction, the operation of a two-pole three-phase synchronous machine. Two-pole machine means the armature is wound for two poles. So, when a three-phase supply is given to the armature winding, two poles are created. One is the N pole, one is the S pole, and these poles are actually rotating in nature. They are rotating at a constant speed of Ns, where Ns is, as I have just told you, it is 120 F by P in RPM, or the same can also be written as radians per second as twice F upon P. This is in RPS. So, as I said, the stator is wound for two number of poles. With a 50 Hz supply, the speed of rotating magnetic field would be 3000 RPM. It is from 120 F upon P, 50 upon 2 is the number of poles, 50 is the frequency of supply, so it comes out to be equal to 3000 RPM, right? So, the stator is wound for two poles. A three-phase supply with 50 Hz frequency is given to the stator winding of the machine. A rotating magnetic field is created, say N1 and S1 are the poles created by the current given to the stator winding of the machine. These poles are rotating at a speed of 3000 RPM, where 3000 RPM is the synchronous speed of the rotating magnetic field. Now, when field winding provided over rotor is also excited with DC supply, it will develop its own magnetic field. Suppose the magnetic poles created by the DC current flowing in field winding are given by N2 and S2. I have already mentioned, we have already assumed that N1S1 is the pole, N1S1 is the pole pair created by current flowing in the stator winding or armature winding of the machine. right? So now when the field winding on rotor is excited by a DC supply, it also produces two poles. Assuming rotor construction to be a two-pole construction, the two poles are given as N2 and S2, which I have marked in the figure. Now one magnet is rotating at ns speed. Which magnet? It is the magnet produced by the stator. So magnet pole pairs produced by the stator are rotating at a speed of ns, and they are having the number of poles n1 and s1, while these at start the rotor is stationary, right? Suppose this is the random position of the rotor at a particular instant of time. What we can see over here, that N1 and N2 are in vicinity, that is like poles are in vicinity. Towards this side as well, S1 and S2 are in vicinity. So there exists a force of repulsion between the like poles here as well as here. As the stator poles are stationary, rotor poles are free to rotate. So the rotor will experience a torque in this particular direction because of force of repulsion in downward direction towards this side, and because of the same force of repulsion an upward torque this side. It will cause the rotation of rotor in anti-clockwise direction. What happens? You see, the field produced by the stator is rotating in clockwise direction. We have considered a particular instant of time. At this particular instant of time, the force acting over the rotor is in anti-clockwise direction, right? If somehow, let us assume, if somehow the unlike poles N1 and S2 or S1 and N2, instead of what I have shown in the schematic representation, if somehow the unlike poles N1 and S2 or S1 and N2 are brought near to each other, the magnetic locking may get established between the stator and rotor poles. And as we know, the stator poles are rotating at a constant speed of ns. So after magnetic locking takes place, the rotor poles 2 or rotor 2 will start rotating in the same direction at the same speed of ns rpm. So as the stator poles are rotating due to magnetic locking, rotor will also rotate in the same direction as that of stator poles, that is the direction of rotating magnetic field, and at the same speed, that is the speed of rotating magnetic field. So the synchronous motor rotates at one and only speed. These motors are the constant speed motors. The speed is dependent upon the frequency of supply given to the motor. If we need to change the operating speed of the motor, we need to change the frequency of supply given to the motor, right? But this all depends upon existing of magnetic locking between the stator poles and rotor poles. They can only rotate if the magnetic locking is existing between the stator poles and rotor poles. But what is the problem here? Practically, it is not possible for stator poles to pull the rotor poles from their stationary position to attain the magnetic locking condition. And because of this, the synchronous motors are not self-starting. We have to assist the motor so that rotor can be brought to the magnetic locking condition. Only after that, the rotor will start following the stator magnetic field and rotor will start rotating at the speed of rotating magnetic field ns, right? So let us see why a three-phase synchronous motor is not self-starting. For this, let us consider a simple two-pole machine. Let us assume that F is the frequency of supply given to the stator winding. It is in hertz. Suppose the frequency is equal to 50 hertz, right? For a frequency of supply of 50 hertz, the time period of the same would be equal to 1 by 50, that is 0.02 seconds. Now, let us see what actually happens inside the machine when a three-phase supply is given to the stator, and at the same time a DC supply is given to the rotor winding. So, considering the rotating magnetic field as equivalent to physical rotation of two stator poles N1 and S1, let us assume that they are the physical poles and they are rotating in clockwise direction. Let us consider an instant when two poles are along the line AB. You can very well see the line AB over here. At this particular instant, arbitrarily, let us consider that this is the position of the rotor poles. Now, at this instant, the rotor is stationary and the unlike poles will try to attract each other, or the like poles will try to repel each other. Under this condition, at this particular instant of time, what we can see is the rotor N2 pole is near to stator N1 pole, and likewise the rotor S2 pole is near to stator S1 pole. Due to this, the rotor would be subjected to an instantaneous torque in anti-clockwise direction, right? This was a particular instant of time. At this instant, this was the position of N1 pole of the stator, this was the position of S1 pole of the stator. So, at this instant of time, what we found, that rotor is subjected to an instantaneous torque, and that torque, direction of that torque is anti-clockwise, right? Now, let us consider the instant just half cycle after this instant. After half cycle, one complete cycle is of 0.02 seconds. The half cycle would be of period 0.01 second. So, let us see the condition just after 0.01 second, that is just half cycle after this particular instant of time. Now, the stator poles are still rotating at the ns speed. After 0.01 second, the stator poles will attain this position. Now, S1 is the position here, S1 position is here at A and N1's position is here at B. Rotor, from previous torque development, in this previous case, what we saw, that rotor is subjected to a torque in anti-clockwise direction. But actually what happens, as the magnetic field produced by the stator is rotating, right? So, rotor, magnetic field produced by stator is rotating. Rotor could not respond to development of this instantaneous torque. Before rotor could respond, the position of stator poles got changed, right? The mechanical inertia, the mechanical time constant is very high as compared to the electrical time constant. So, the changes taking place in electrical circuit are very fast. The rotor, being mechanical in nature, cannot respond that much fast, right? So, what happens after 0.01 second, as rotor could not rotate in 0.01 seconds time, the new force that is now exerted over the rotor is shown to be in clockwise direction. But again, if we consider the very next instant of time, you will find that what happens, the position of stator poles will again change. Earlier, the rotor was subjected to a torque in anti-clockwise direction. Now, the rotor is subjected to a torque in clockwise direction, and again, after 0.01 second time, the rotor would be subjected to a torque in anti-clockwise direction, and so on. This process is getting repeated again and again after every half cycle, right? So, what actually happens? Rotor cannot respond to torque development in any direction because of this reversal of the polarity, because of this continuous variation in the polarity of field produced by the stator, and because of this, rotor cannot rotate from its initial position of rest. But somehow, if we assist rotor to attain this particular position and with a rotation which is somewhat less than the synchronous speed of the motor, rotor poles will definitely get attached with the stator poles. That is, the magnetic locking will then take place between the stator magnetic field and the rotor magnetic field, and rotor will start rotating. So this is the reason why a three-phase synchronous motor is not self-starting. Right? Now let us see how to make the three-phase synchronous motor a self-starting machine. For this, there are certain methods. There are certain methods which will help the rotor to attain the magnetic locking condition. Right? These methods are using pony motors, using damper winding, as a slip ring induction motor, and using a small DC machine coupled to the three-phase synchronous motor, right? So for magnetic locking, let us first understand what is required for magnetic locking to take place. For magnetic locking to take place, it is necessary to rotate the rotor at a speed which is very near to the synchronous speed, and under that instant of time, if at that instant of time when the speed of rotation of the rotor is near to the synchronous speed and the conditions are favorable. The meaning of favorable condition is if unlike poles are of stator and rotor are near to each other. So when the speed of rotation is near to synchronous speed and when the favorable conditions exist, the rotor will pull into the magnetic locking. Once rotor is magnetically locked with the stator magnetic field, rotor won't be having any other option but to rotate with the stator produced rotating magnetic field at the same speed, which is the synchronous speed of the machine. So let us now consider various methods which are used for starting the three-phase synchronous motor. The very first method here that is being discussed is using pony motors. In this method, actually the rotor is brought to the synchronous speed with the help of some external device. This external device is actually an external machine. It can be a small induction motor as well. This external machine is said to be the pony motor. This external motor is said to be the pony motor. This can be a DC motor as well. Once the rotor attains the synchronous speed, the DC excitation to the rotor is switched on. Once the synchronism is established, establishment of synchronism means once the speed of the rotor is near to the synchronous speed and magnetic locking between rotor and stator took place, this is said to be the synchronism condition. Once the synchronism is established, the pony motor is decoupled mechanically. The motor then continues to rotate like a three-phase synchronous motor. The second method is with a damper winding, by using a damper winding. In a synchronous motor, in addition to the normal field winding, an additional winding is provided over the pole faces. So here in the figure what you can see is, this is the normal DC field winding. In addition with the DC field winding, another winding is provided over the pole faces of the machine. This winding is said to be the damper winding or damper bars. Damper winding is actually just like the squirrel cage winding of a three-phase induction motor, right? So in addition with the normal field winding, a winding is provided over the pole faces. This winding is said to be the damper winding. The winding actually consists of rotor bars which are placed in slots over the pole faces. These are the slots provided over the pole faces, and in these slots are placed the copper bars. These copper bars are short circuited with the help of end rings towards both sides of the rotor of the machine, right? This additional winding on rotor is called the damper winding. As I just told you, this winding is short circuited and it acts just like the squirrel cage rotor winding of an induction motor. The schematic representation is shown over here. Now, let us see what actually happens when a three-phase supply is given to the motor. When we start the three-phase synchronous motor, like a three-phase induction motor, we do not provide the DC excitation to the rotor of synchronous motor initially. So, initially when supply is given to the stator winding, what happens? A rotating magnetic field is created. This rotating magnetic field, just like a three-phase induction motor, this rotating magnetic field produces an EMF in the damper winding. Damper winding is a closed circuit. So, a current, because of the induced EMF, a current starts flowing in the damper winding, which gives rise to its own magnetic field, and just like a three-phase induction motor, a torque is developed over the rotor in the direction which is same as the direction of rotation of the rotating magnetic field produced by the stator, right? So, what happens? Rotor itself started rotating, right? Rotor started rotating just like the rotor of a three-phase induction motor. This is the direction, for example, this is the direction of rotation shown for the rotor. I said rotor will start rotating in the direction of rotating magnetic field. This must be the direction of rotating magnetic field, that is anti-clockwise direction. Now, under these conditions, the rotor must be operating like a three-phase induction motor's rotor at a speed which is somewhat less than the synchronous speed, right? Now, the supply to the rotor field winding is switched on. It will develop the magnetic poles over the rotor. Now, we have got two magnetic fields, one produced by the stator, and now rotor have got permanent magnetic poles. Rotor have got the magnetic poles so created. When the conditions are favorable, that is, when the unlike poles of stator and rotor are in vicinity, the rotor will pull into the magnetic locking, and after that rotor will start rotating at the speed of rotating magnetic field's speed, that is synchronous speed ns equals to 120 f by p. And what happens? Let us see. When rotor started rotating at a speed of ns, let us see what happens to these damper bars. The damper bars provided over the rotor pole faces are also rotating at ns speed. So, there is no relative motion between the rotating magnetic field and these damper bar conductors. So, no EMF will get induced in these damper bars, and hence no current would be flowing over here, and the motor is operating like a three-phase synchronous motor. Now, the third method is to start the motor like a slip ring induction motor, three-phase slip ring induction motor. In previous method, we started the motor like a three-phase squirrel cage induction motor. In this particular method, we are starting the three-phase synchronous motor like a three-phase slip ring induction motor, right? So, in the previous method of starting, the synchronous motor was started like a squirrel cage induction motor. What is the problem with that type of starting? The only problem is a high starting torque cannot be developed. So, to achieve this, instead of shorting the damper winding, it is designed to form a three-phase star or delta connected winding, and the three ends of this winding are brought out through the slip rings. An external rheostat can be introduced in series with the rotor circuit. So, which rotor circuit? The rotor circuit formed by the damper winding. So, damper winding in this case would be in the form of the winding, proper winding, either connected in star or delta, or for the purpose of developing high starting torque, just like a three-phase slip ring induction motor, an external resistance can be connected in series with this damper winding, right? So, when motor attains the speed, just like a three-phase slip ring induction motor, at the time of starting, the high resistance is capped in the damper, high external resistance is capped in the damper winding circuit. When motor picks up the speed, gradually this resistance is reduced, and when motor picks the normal speed, that is somewhat less than the synchronous speed, the resistance, external resistance is cut out completely from the damper winding circuit, right? Now, when motor attains speed near the synchronous speed, DC excitation is provided to the rotor and motor gets pulled into synchronism and starts rotating like a three-phase synchronous motor. The damper winding is short-circuited during this condition with the help of the slip rings, right? So, the additional initial resistance added in the rotor does not only provide high starting torque, but it also limits the high inrush current which is there as we are starting the motor like a three-phase induction motor. So, it also serves the purpose of rotor resistance starter when motor is being started like a three-phase slip ring induction motor. Another method is using a small DC machine. Many a times we know the large synchronous motors are provided with a coupled DC machine. This DC machine is used as a motor to rotate the synchronous motor at synchronous speed, and then excitation to the rotor is switched on. Once the motor starts operating like a synchronous motor, the same DC machine which was acting as a starting machine for the motor is now operated like a DC generator which is set to be the exciter of the machine. The same generator actually provides DC supply to the field winding of three-phase synchronous motor. So, these were the four methods of starting a three-phase synchronous motor. Now, let us discuss another important topic in three-phase synchronous motor. It is the V-curves and inverted V-curves, right? V-curves and inverted V-curves are actually the result of a particular behavior of a three-phase synchronous motor which is obtained when we vary the excitation given to the synchronous motor. We know that a synchronous motor is a doubly excited machine. We also know the basic construction and operation of the motor. We know that a three-phase supply is given to the three-phase armature winding provided over the stator of the motor, and a DC supply is given to the DC winding provided over the rotor of the machine, right? Now, if we vary the excitation, the DC supplied to the rotor winding of the machine, a particular behavior of the synchronous motor is observed. What is that behavior? If we vary the excitation given to the field winding, with respect to that variation, there is a corresponding variation in the armature current and armature circuit power factor of the machine. So, here we will discuss the effect of variation of field current on armature current and power factor of synchronous motor. The outcome of this will give us the V and inverted V curves of synchronous motor, right? So, as I told you, a synchronous machine is a doubly excited machine. A synchronous motor is a doubly excited motor. Its armature winding is energized by AC source and field winding is energized by DC source. Now, When motor is working at constant Vt, Vt is the voltage given to the armature winding of the machine. When the motor is working with a constant Vt, the resultant air gap flux remains substantially constant as demanded by the constant terminal voltage Vt. To justify this, let me just write down the EMF equation of the machine. We know that induced EMF, in case of motor, we call this EMF to be the back EMF of the motor. Back EMF is induced in the armature winding of the machine, right? Now, let us write down the equation of the same. It is 4.44 phi, which is flux per pole, F, kW, right? kW and pH, right? So, instead of kW and pH, I can write 4.44 phi F and pH dash, and pH dash is the effective number of series connected turns per phase, and pH is the number of turns, series connected number of turns per phase. kW is the winding factor of the machine. You also must be knowing that kW equals to kd multiplied by kp. Kd is the distribution factor, Kp is the pitch factor. So, taking into account the distribution factor and pitch factor, this is a constant once the machine is constructed, right? Once the machine is manufactured, Kw is constant, right? So, kW multiplied by NPH gives us the effective number of turns, effective number of series connected turns per phase, right? So, from this equation what we see, it is 4.44 phi F and pH dash. Supply frequency is kept constant. Terminal voltage is also constant. It means, what is the difference between terminal voltage and induced EMF? The difference is of the voltage drop in the self-impedance of the armature circuit. That voltage drop is actually I1Z1 voltage drop. I1Z1 voltage drop is negligibly small as compared to the magnitude of the terminal voltage or the back EMF. So, we know the terminal voltage is approximately equal to the back EMF. So, if the terminal voltage is constant, this right hand side portion of the equation have to remain constant. What do we have over here? It is NPH dash, which is a constant. F is the frequency of supply, which we are maintaining constant. 4.44 is a number, is a constant. Phi is the flux. So, for a constant terminal voltage Vt, the air gap flux must remain constant as demanded by the terminal voltage Vt, right? Now, let us see. The resultant air gap flux is actually established by cooperation of both the DC given to the field winding and the AC given to the armature winding. If the field current given to the field winding is sufficiently enough to set up flux phi in the air gap of the machine, we say that the motor is normally excited. When motor is operating under normal excitation, there is no requirement of magnetization or of lagging reactive volt ampere from the armature circuit, and hence the armature operates at unity power factor, right? So, under normal excitation field current condition, the armature circuit operates at unity power factor, and later on you will find that under these conditions the magnitude of armature current is minimum. Now, let us consider the case if the field current is made less than the normal excitation field current. That is when the motor is under excited. What happens? Deficiency in the flux must be made up by the armature winding MMF, and in order to do that, the armature must draw a lagging reactive volt ampere or a magnetizing current to fulfill the deficiency of the flux caused by the underexcitation of the machine. This causes the operation of the motor at some lagging power factor. Now, let me show you the two conditions with the help of the phasor diagram, starting with unity power factor operation. Vt is the terminal voltage taken as the reference phasor. Under the conditions of normal excitation, I have told you that the armature would be operating at unity power factor. So, some amount of current, let it be current IA2, is flowing in the armature circuit. The current would be in phase with the terminal voltage Vt, right? The phasor sum of terminal voltage, the phasor sum of excitation EMF under this condition, which is EF2, and the voltage drop IA2 excess can be shown to be equal to the terminal voltage Vt, right? Now, under second condition, what we have done? We have changed the excitation. We have actually reduced the excitation of the machine. So, with this reduced excitation means reduced flux phi. A reduction in flux phi would be causing a reduction in the induced EMF. So, the new induced EMF is EF1, let it be. EF1 and the voltage drop IA excess will give you the terminal voltage Vt. Now, you see, excess is a constant. There is a variation in excitation EMF EF. Terminal voltage Vt is constant. So, because of variation in this and excess being a constant quantity, a constant parameter, current IA must change so that the voltage drop IA1 excess plus EF1 gives you the same terminal voltage Vt. So, under these conditions, it can be seen that the current flowing in the armature got increased to a level of IA1. You can very well see that the magnitude of IA1 is more than the magnitude of IA2. Under these conditions, the current is flowing at a lagging power factor, and that power factor angle is theta 1, right? Now, let us consider the third case. One more thing which I would like to mention here is, as we are not changing the power, we are not changing the load at the shaft of the motor. So, the amount of electrical power drawn by the motor from supply, amount of real power drawn by the motor from supply will remain constant. That real power is given by either Vt Ia cos theta or EF Vt upon xs sin delta, right? So, Vt and xs are constant, right? EF sin delta actually varies, so that if there is a variation in EF, that variation would be accompanied by a variation in the load angle delta, so that EF Vt upon xs sin delta remains constant. Likewise, here Vt is constant. If there is a variation in current Ia, it must be accompanied by a variation in the power factor, so that Ia cos theta remains constant. Under unity power factor condition, this was the in-phase component of current, right? Under lagging power factor operation as well, this in-phase component must have the same magnitude. Now, let us consider the third case. The third case would be the case of overexcitation. Overexcitation means an increment in the field current given to the motor. So, the excess amount of flux must now be neutralized by the armature winding, as the air gap flux has to remain constant as demanded by the constant terminal voltage given to the motor. So, to do this, demagnetizing component of current is drawn by the armature of the motor. A demagnetizing component of current is the component of current which leads the voltage by an angle of 90 degrees. So, now the armature current would be having two components, one in-phase component with Vt and another one is the leading component by an angle of 90 degrees. The resultant of these two gives us the new current Ia3, and you can very well see the magnitude of Ia3 is different. The angle of current Ia3 with respect to voltage Vt is theta 3. Say for example, with increased excitation, the new induced EMF is EF3 and the phasor sum of EF3 and IA3 axis gives you the constant terminal voltage VT. Under these conditions, the motor is operating with an increased armature current and at leading power factor. To conclude, if we see the effect of variation of field current on armature current IA, and if we see the effect of variation of field current on cos theta or cos phi or the power factor of armature circuit, we will have these two graphs. This is showing the relation between the armature current and the field current, and this one is showing the relation between the armature circuit power factor and the field current of the motor. The first one is said to be the V curves and the second one is said to be the inverted V curves of the machine. You can see this point corresponds to the normal excitation field current. Towards this side, the machine is overexcited. Towards this side, the machine is underexcited. Same holds good for this curve as well. So what you can see over here, the normal excitation, under normal excitation, armature current is having minimum value. Beyond this, overexcitation condition gives you an increment in armature current. Underexcitation condition also gives you an increment in the armature current. Likewise, you can see the effect in the power factor too. So this is said to be the V curves and this is said to be the inverted V curve of three-phase synchronous motor. So that's all for this lecture. Thank you.